Okay. So we do have a square box. It's similar to the one we did last time. Have a square box, and let me show that. And there's 3 charges. There's 2 negative and 1 positive, and the positive is between the negatives. So I'm gonna draw this as positive, through this as negative, another negative in here. Let's also give this distance r, and we want to find what is the electrical potential in here, this point. What to do? Does anyone know how to start?
Would you draw vectors accordingly, like going into the negative and giving out from the positive?
Okay. Say that again, and slowly, and go step by step.
Oh, so you're going to use the vectors from the charges. So if it would be negative, it would be pointing inwards, and if it was positive, it would be pointing outwards.
Okay, so I'm gonna take here talking about that. So, I mean, there is a vector between the point that we want to see what's the potential in here and this charge. So, you mean I have to draw like this?
Yes, or we are trying to find the, no, not the field, the potential.
Okay. But to find the potential, like, what other, is there anything else I need to find? Like we know that, like this equation, for example, we have that U, the potential energy, is equal to QV. This is a way. We also have what? We also have that E is basically, in a way, like in the book it says negative dV over ds, which you can also write as, it's not always true, only like for point charges and spheres. You can say that the electrical field is equal to negative V multiplied by R. But this is in a really special case. Okay, but do you have an equation for V? Let's start with that. Or should we find the potential energy or the electric field? Then from these we can find the the V.
Would V equal U over Q?
Okay, would V equal Q over U?
No, U over Q, because if we divide the left
Oh, you
hand
mean
side.
this part? Yeah,
Yeah.
you can do that. Yeah, like you say, V is equal U over Q. Okay. Well, what is your U at this point?
Let's see. Would we only use one charge or multiple?
Well, you do have 3 charges acting, like 3 charges, and they would have a specific, make a result of electric field in here. So from the 3 charges, you need to find that. But to find that 3 charges, what you can do is you can find like the electric field or the potential energy acting at this point individually, then add them. You can do this or you can do that. It's up to you. So you want to go this way, that V is equal to U over Q, right?
Yep.
Okay. So we want to find what is U. U is equal to what? We're going to call it U total. So if it's U total, it's going to also be U total. Okay. So we can say, if we gave this, let's say it's particle number 1, this is particle number 2, this is particle number 3. Okay. We can say that U total is equal to what? Yeah, is equal to what? First of all, is U a vector or a scalar?
Wouldn't it be scalar?
Yes, indeed. So from that, I can just say that the U total is equal to U1 plus U2 plus U3. Does that sound okay?
Yep.
Okay. So now we want to find what is U1. What is U1 is going to equal to? U1 is going to be the potential energy from this point at that.
So would 1 be considered the origin?
So 1 would be considered what?
The origin. Like if it's scalar, then.
That's a good question. Let's say that your origin is infinity. So that when you calculate any potential energy, it's usually the change in the potential energy. So if you set like something like x where we need to find it when it's u at infinity, usually because like if you have what? If you have a charged particle, let's throw a charged particle in here. It would have electric field everywhere. Like it's going to be pointing up, to the right, down, and so on, right? And the electric field of that charge, its E is equal to what? It's equal to KQ over R squared, right? And its U is equal to KQ over R. Is this right? Actually, yeah. Actually, this is not fully complete. Yeah, if this is a point, and let's say I do have it like a test charge, came from infinity and came to here. So the U then would be, let's call this Q prime, would be Q prime Q, this would be K over R. So when Q, if it was at infinity, this R would be infinity, and anything over infinity is just 0. That's why we take infinity as our reference. So the whole potential energy goes to 0. Is that okay?
Yep, so the R basically gets so big that it equals 0.
Yeah, it gets so big that whatever is there makes it like 0 point however many zeros. Like, so like if this was infinity, like yeah, as this goes to infinity, that means U. Okay, so let me write that. So then we have the limit of U as R goes to infinity is 0. Yeah, this gets too big, and when you divide anything small over something big, it gives you 0, basically.
Gotcha.
Yeah, so that's why we take infinity as our reference point. So because you have the change in U yeah, is equal to ux minus u infinity. But if u infinity is just 0, you only have equal to ux. Okay, so what is u1 equal to?
So would it be k times q over r?
Yes, so first we need to give this, let's call it q prime. So
Oh, it's q prime, yeah.
yeah, q prime over what?
Over r?
Okay, well, what does this r represent?
Would it be from the point charge 1?
Well, if you have the site itself as r, the distance from the positive charge to this q prime, it's not going to be r.
Would it be root 2r?
Yes, indeed. Yes, indeed. Be root 2 r. Okay. Then what is u2?
u2 would be k times q prime times q over r.
It's negative q though, because this
Right.
is negative. Yeah. Same thing will be for u3 will be k minus q prime q over r. Okay. So with these, we do have that the u total is equal to, you can just take the k q over r outside. Well, you know what? Let me rewrite it. Write the whole thing. So it will be kq prime q over root 2r plus minus 2 kq prime q over r. Is that okay?
Yep.
Okay. We can then just take the k, q prime, and q and r outside. So we'll have k as a common factor, I mean, over r. That would then equal to 1 over root 2 minus 2. Is that right?
Yep, because you just grouped them all to be multiplied together instead of adding, right?
Yes, indeed. So now from this, how can we get now the potential? Like this is the potential energy at this point. But now, what is the potential electric potential, which is V?
Well, we can just divide it by the charge, right? Like
Yes,
you.
indeed. So that means that V is just equal to U total over Q prime, which is equal to KQ over R 1 over root 2 minus 2. So this is a way to do it. Another way, which you could have just from the beginning said that, the V total is going to equal to V1 plus V2 plus V3, where you have V1 is just going to be the same thing as the U1 except for the Q prime. And that's why in the question I didn't give you any charge in here, because this Q prime is going to get canceled anyway. So you can just say V1 is equal to K Q over root 2R, and V2 is equal to K minus Q over R, V3 the same thing. So now V total is equal to kq over r, take that outside, we will have 1 over root 2 minus 2, which is exactly the same. So they are basically the same steps. The only difference is that we kept using the q prime all the time and just came here at the end and we canceled it. We can just like cancel it from the beginning and get doing the same steps. Okay, so does anyone have any questions about this? I will take that as a no and jump to the next question, which is quite sad because I thought you guys knew how to do Gauss's law. Okay, so we need to find the electric field potential energy and electric potential outside of a solid sphere, and that sphere has radius of r and charge q, and we need to find all of these as a function of r, distance r. So let me draw. Okay, might as well. This is r, and say that overall it has charge of q. We want to find the electric field of that. How can we do that? Oh, I actually should be the one who's telling you that because we're doing it in a Gaussian way. Okay, so Gauss's law is really easy. It's really obvious, like not really obvious, but it's really easy to deal with. You can just jump all of that into, like, you can just, if you know what is the electric field of a solid sphere, it's basically this. Like the electric field of a solid sphere is equal to k q r squared. That's what it is. But we're gonna do the same thing with Gaussian law and see if it gets us the same thing. So basically, the Gauss's law says if you draw anything, so I'm just gonna draw a sphere, like another sphere around our first sphere, but that shape has to be closed. Okay. It says that the integral of E multiplied by the so you're going to integrate over an area is equal to q closed enclosed over epsilon. So basically what it says, if I have any Gaussian, like any shape that I drew, and I want to know what is the electric field inside of it, I can find the electric field that's crossing it if I found the area of the surface area or the area of the Gaussian and divided by the charge that it is enclosing. So whatever charge is in it, I'll just divide it by that. So we can do that. First thing we say, what is Q? What is, for this Gaussian, what is the charge that is holding inside? And the charge is holding inside is the charge of the solid sphere, which is Q. So we have Q enclosed is just equal to Q. So now we need to find, so now we have E dot dA is equal to Q over epsilon naught. We can say since the it's a sphere and sphere are symmetrical, you can just say that the E would be constant and just take it outside. You would have this integral. And then the surface, this integral is the surface area of a sphere, and the surface area of a sphere is just equal to 4 pi r squared. Now we have E multiplied by 4 pi r squared equal to q over epsilon naught. That means that E is equal to 1 over 4 pi epsilon naught qr squared, which is also known as kq over r squared, which is the same we had over here. So that's basically what Gauss's law says, or how it works. But then it's powerful because you can apply it to any shape. So if you have any weird shape, you can just apply the same thing and you would know. Like if I give you, I don't know, give you shape like this, and it has charge of 2q, let's say. Same thing if I just had a, like if I drew a sphere or a circle around of it and applied the same law, I would be able to get what is the electric field coming out of this thing. That's just what it says. Okay, so now we do have the electric field. We want to find what is the so now we have electric fields as a function of r, so it's kq over r squared. We need to find what is the potential energy also as a function of r, and as the previous question, we're going to take our reference being our origin being the infinity. So now this is a question to you, and you do have the knowledge for it. What is u? How can we find u if you have the e? Okay, well, the nice thing about solid spheres that once you're outside of them, you can just treat them as a point charge, which is the same thing. Like this equation is the equation of a solid sphere and also an equation of a point charge. So if you, let's say now, let's consider this sphere just as a point charge. How to find the potential energy of a point charge? It's the same thing we did here. Okay, so again, if you do have a point charge, if I just like gave you a point charge, let's call it plus, what would be the equation of its potential energy? Pointing outwards. I have like a test particle. Let's call it E. So it was here at an infinity. Let's say it's an electron. Then crossed all the way. So it came here. So now it's also the same E. What is the equation of it? What's potential energy does this E have or got?
0.
Well, not really, because a potential energy is the change in U, which is equal to U final minus U initial. And we do have that the U final itself is equal to this equation. So it would be K Q multiplied by Q of E, which is negative let's call this distance, I don't know, which is, yeah, let's call the distance, well, the distance r, so this distance is r. This distance is r, so it'll be r. Well, u infinity, so u initial is going to be kq, k negative q qe over infinity. So that's going to equal to 0. So that means that our change in u just equal to k q q e negative over r. So same thing. You can say for a positive charge, the u of this thing is also going to equal to k q q over r. And another way to know that, what is the equation of an electric field? The equation of what is the units of electric field? The units of our electric fields are what? Call this to say, I want to find the units. Are equal to what? What are the units of electric field?
So newtons per coulomb?
Yes, indeed, newtons per coulomb. And we do know what are the units? What are the units of potential energy?
Joules.
Yes, indeed. And joules is also equal to Newton meters, right? Because joules is work and work is force multiplied by the distance covered. So it seems if I want to get from E to U, I need to multiply by C, so I can cancel this C and also multiply by an M, by a distance. And that's exactly what we did. So if you just multiply by another C, so if you multiply, like put any charge, multiply by any charge, which is going to be Q, can cancel U, your C, and then also multiply by a distance, which is going to be the R. So now the R squared is gone, now we only have R. So that's exactly what it does. It's pretty much the same thing. You can always know, like always check, like what you have makes sense or not based on the units. Okay, so now what are the units of electric potential?
Would it also be newtons per coulomb?
Not really, no. There are a little bit more than that, a little bit different than that. They're actually joules per coulomb. Because if you remember what we did before in here, we had the U and we divided by Q. So you have the U just divided by Q, which is a charge. So it's going to be joules per coulomb, which means how much energy it takes to move 1 coulomb. So let's go in the next example, for instance. Let's say if I have a what? If I have say like this is 2 plates. Okay? And do you know what's the equation of a plate? The electric field of a plate? Oh, oops. This should be
would it be the density over E naught?
The density over E naught. Yes, indeed. Okay, so we do have the electric field. E is equal the density, which I do believe is going to be that, over E naught. Is that right? Density is charge, which is Coulomb, over an area. Yeah, that sounds right, I think.
Yep, that's right.
Yeah. Okay. Okay, yeah, so this is our E. Let's say I do have a proton in here. Okay? Then it moved to here. Let's say it moved distance, I don't know, like R. Okay? Would its energy change?
I don't think so.
Why?
Because does it not have anything to do with position?
Yes, yes indeed. So what? Yes indeed. Yes indeed. Because in a way, the potential energy is seeing how much change or how much force do you have to do to make this proton move, right? But when you like looking in here in this example, we had the electric field like from the other day. We had the electric field pointing this way. I do remember that. Let's give it green, I guess. No, we already have green. This thing. Remember that we had E pointing in this direction at this point. So when we had our proton at a distance and come here, we had to apply force. You had to move it. You had to apply some work. You had to apply force for a specific distance, which is work, and that work is translated into potential energy. Okay? This is how much energy it puts in this charge to get to this place. That's why we always see the change in potential. And that's why we set it to infinity, so this just cancels. But since if you have the electric field is the same everywhere, not really applying any force, because you're not going against or with the electric field. Electric field just as it is. So you can say, since since the electric field, change in the electric field is just zero, you're not doing any work. So the potential energy is just going to be zero. Like the change in it, like it didn't really do any work. You didn't go against or with the electric field because the electric field is just as it is. Okay. Does anyone have any questions? Okay, what readings do you have? we can go over one example in that might help you for tomorrow.
We have 26.3 to 26.7.
26.3 to 26.7. Okay. So let's do that. Let's just take a question. Okay, we can start now by an easy one then. Let's see how much time we have. Okay, so how much work does it take to charge escalate to do oh yeah, how much charge escalate do to move 1 nanocoulomb of charge from a negative terminal to a positive terminal of a 1.5 battery. So let's just draw that. Which question is that? 17. So chapter 26. Chapter 26. Question 17. So how much okay, so let's say I do have 1.5 battery, 1.5 volts. So that means if this is 0 volts, it's going to be 1.7 volts. So we have a charge Q of 1.5 microcoulombs. Want to move it from the negative to the positive. So it's here. I want to move it this way. And it's 1 microcoulomb. Okay, and we need to find how much work. Okay. So first things, always see what's your equation. So this is section 26.4. Let's go see our equation. This is boring. Okay, so our equation, a change in potential, the change in the potential electric potential is equal to the negative of E multiplied by S. That's basically what it says. Yeah. So we have V is equal to negative the integral of E ds. We can say, since this is just a straight line, it's going to equal to negative E change in S. Is that okay?
Yep, I haven't done the reading, so.
Well, hopefully this will make it easier, I guess. Okay, so this is V. And we need to find what is the work. We'll get to that in a bit. Okay. So one thing we can do is we can find what is the electrical field is. So E is equal to negative V over delta S. That's going to equal to, did it say what is the distance? Feels I'm doing something wrong. This E, the electric field, is this E, the energy. Yeah, this V is the electric field, pointing from the positive towards the negative. Yeah, so it's going to be the change from V positive to V negative. Okay. Well, that's okay, because we can always find, we know that like we can find the V, and from the V we can always find what is the what is U. What is U? Right, but we do need the electric field though. Is there something missing? Give us Q. Okay, we do know that U is equal to VQ. Also, we do know that E is equal to, in this case, E is equal to what? E is equal to Vs. That's useless. V also is equal to, it should be negative. Also should be U, Q, S. Okay, there we go. Oh, that's really easy. Okay, I don't know why I said that's really easy. Okay, so now we do have that negative Vs is equal to UQS. We can just mean that negative V is equal to UQ. Yeah, which we just wrote over there. Yeah, so that means that U is equal to negative VQ. And we have the V is 1.5, 1.7, negative that multiplied by the Q, which it gave us. It was just 1 microcoulomb. So it's going to be 1 to the power of negative 6. Yeah, that should have been more obvious. This is equal to negative 1.7. I do believe this is negative, honestly. I'm pretty sure this is negative. Always check. I'm pretty sure, because it's going from positive to negative. And it's the positive charge. So the work, it asks us for how much work does the charge do. So actually the charge is not doing any work. The charge is taking energy. So it's doing negative the work. Yes, yeah, it should be negative actually. Okay, so we were okay. Just leave this as it is. Well, it's going to be negative 1.7 multiplied by 1 to the power negative 6, which is just negative 1.7 microjoules. I want to say questions. We didn't really need all of this.
So it says U equals negative VQ, right?
U is equal to negative VQ. I do believe so, because it's not gonna do any work. Because if you have a positive charge and it says goes from the negative terminal to the positive. Oh, never mind then. Okay, well then it depends where it's going. So if you have it in the negative and it's going to the positive, the electric field is pointing this way. The electric field is pointing this way, right? And this charge is positive. This is, let's call this positive, and this is negative. So if it's positive and going towards the positive, so it actually has to do work. It's going opposite to what it wants. So actually, this should be, the negative should be removed. Yeah, because it's doing work. This is how much work it is going to do.
Sounds good. It's just a little hard to distinguish the U's from the V's. It's hard to draw.
Yeah, finding the work to know is it work done or is it work by? It's and if it's negative or not, that can be a little bit tricky. Okay, I don't really have any questions like ready or set. This was mainly being you guys asking me questions. So you're free to go. If you want me to go over something, let me know. Just stop recording here.